Okay, thanks a lot, Steve. And first of all, I'd like to thank Steve for inviting me here. I'm really happy to be here. Looking forward to all the other talks and to interacting with everyone here. So just to introduce myself, my name is Siddharth Rajan. I'm from Ohio State University in the EC and MSc departments. I'm going to talk about results from many groups, but there is going to be probably a little bit more disproportionate amount from my own group. And so a lot of the work is done by my group members. Chung Hee is right here. Sriram, Edwin, Lashkar has left a couple of years ago. And as well as many other groups at OSU, Yiying Wu in chemistry, Roberto Myers, Jinwoo Wang is our TEM expert, and Roland, who we're working on, who also shares our MBE with us. So before I start, and of course, I'd like to acknowledge our funding from Air Force and NSF. So before I start, just a quick introduction. This is our group here. We actually work mostly on gallium nitride, wide and wide bandgap materials, but we are also interested in 2D, and maybe a bit later in the talk, you'll see why we're very interested in 2D materials. It's becoming a very important focus in our group. And also growth of 2D materials is becoming a very important focus. Just a quick research overview. We're a device group, and so our final objective is to make devices, mostly electronic, recently also some opto devices with gallium nitride. And, but we do growth of materials. So we have several growth chambers that my group operates. So we have a 3-nitride chamber, which was the oldest one. This is the home of the chamber. It's a Vico chamber. And so this is basically where where it was born. We have 2 more, which are right now like babies. One is the gallium oxide chamber. Gallium oxide is also a wide bandgap semiconductor. And although it's not van der Waals bonded, interestingly, it does have a structure that's similar to layered. You can actually exfoliate it, so it's kind of interesting. And then finally, of course, we have another MBE chamber for, this is not the same MBE chamber. These are 2 different MBE chambers for growing selenides, 2D materials. And I'll present some of our recent data from this on growth of 2D materials in this talk. And we also work on CVD of MOS2 separately. This is with Yiying Wu. And so all our growth is really driven by what we want from our devices. And so you may see that we choose certain things to work on, certain materials, because we're driven by devices. So when I started, I said, well, yeah, I'd love to give a tutorial on growth of 2D materials. Then I started thinking about it. I said, oh my God, it's really hard to give a tutorial about growth, right? It's the hardest thing. You can give about devices, transport. Growth is the hardest thing to talk about because, you have to actually go do it. So when I started putting it together, eventually I came up with an outline. I want to introduce what first we want from 2D materials. What are we looking for? When will we know that we're done with the material? And I'll talk a little bit about some phase diagram issues with these, which are kind of interesting. And then I'll just talk about some of the things that happen during MBE growth, CVD growth. And hopefully, as I talk about some of these examples, you can see some of the issues that are there that are maybe unique to 2D materials, but many of them are not unique to 2D materials. They happen in epitaxy of any material, anytime you do epitaxial growth. I think 2D materials are special because they were not started by material scientists and growers. The field was started by chemists. And so the growth is proceeded in a different way. Now we have material scientists, device engineers getting interested. So now there's some other aspects we'll be thinking about. And then finally, I'll talk about some work on doping. And I had to put in some of our device results. So I'll put them in at the end, okay? Just to show that the things we do actually do work. So this is some very nice pictures from this paper, which show basically all the different 2D materials that are available to us. And I know it looks like, out here you're getting systems to grow a lot of these, like the phosphorines and so on, which are very interesting. But if you look at these, this is really so many materials. And it's really hard to wrap your head around, first of all, which ones are important, and secondly, how do you grow them? So it's a huge problem. And I think it's very interesting because as everyone agrees, there's going to be many applications that can come out just from the diversity of the properties. There's, of course, I haven't listed here, but there's magnetic properties. There may be some correlated effects. and so on. So there's many interesting things that can come out. And so growing 2D materials or growing heterostructures of 2D materials is going to be very interesting going ahead. Now, I think Eric Popp was supposed to give an overview of all the applications, but okay, so, but anyway, so I'm going to try to give a very short one, just to say that I think the motivation is that there's so many, and I think out here, I know you're working on some of the digital applications for logic and so on, using 2D materials. I think that's very interesting. I'd like to say what we are interested in. Of course, there's also opto and large area, flexible, and so on. One of the things that we are very interested in is actually combining 2D materials with 3D materials. Because we already work on 3D materials, and we think that 2D materials can basically allow us to integrate different band gaps with less lattice matching constraints. Okay, so there's still lattice matching. I'll show later. We can't completely move away from lattice matching, but there's less constraints. And so we can take advantage of some complementary properties which we have really wanted to see in 3D semiconductors like gallium nitride, zinc oxide, gallium oxide. And so we can combine basically wide band gaps, which high breakdown fields, high temperature operation, with 2D materials, which can basically give you lower band gap materials. So it's very hard to combine low band gap with wide band gap. And another very interesting way is actually a mechanical thing, which is using 2D materials purely as a mechanical transfer. So I'll show later, people have done very nice work making gallium nitride devices on a 2D material, then releasing it. Essentially now you have something that can go on an arbitrary substrate. It can go anywhere. And this is really interesting. If you are familiar with the GaN field, we are so tied to the substrate, sapphire or silicon carbide. If you can move it out and put it anywhere, suddenly you have a very powerful technology. And so, of course, when it comes to growth, these two issues are different. Whether you want to grow 2D on 2D or you want to grow 2D on 3D, obviously it's going to be different because in one case you have no dangling bonds, in the other case you have dangling bonds. So you have to think about how you're going to initiate the growth. And I'll talk about that a bit later. And so, now, just to give an overview, there's, of course, many different ways of synthesizing materials. You know, there's the oldest one, which kind of originated the field, I think a long time ago, but with a lot more attention since the beginning of 2000s, was mechanical exfoliation. And this is a very nice way of actually finding new materials, studying their properties. I think it's really an amazing tool to do it. And I know that it's very difficult. It's not easy to do it. It takes a lot of skill. So those of you who are doing it are probably very skilled at achieving that. But I think it's probably agreed upon now that it's very difficult to make this into a manufacturable technology. So if you really want to make, you know, if you want Intel or Texas Instruments or Raytheon to come in and actually make devices and sell them, we probably need a large area, you know, centimeter, inch scale kind of technology. And for that, we need more traditional growth methods like CVD or MBE. And so there's also been a lot of work, especially in CVD. This is just one example. And now I should say here that I read a lot of papers trying to prepare for this, and I realized I can't cover all the field in a proportionate way. Okay, so if I know there's probably going to be very important papers that are missed out, but I'm just trying to give examples in 45 minutes or something. And so CVD, there's been a lot of work. Okay, a lot of the work, the result is this, which is basically a small area. It's still small area. But recently, there's been some larger area work that's come out, which is very good. Now, the new method, which I'll show you is not so new, is actually MBE. In the last 3 years, several groups in Greece, China, and the US, I'll talk about them, have been trying to use MBE to grow 2D materials. And I think there's always been CVD, MBE, which is better. I think both of them will have some advantages and disadvantages. Eventually, when enough people work on them, they kind of converge. This is what happened in other material systems. Material starts to look almost the same. It doesn't really matter what you use. You can make good material with both. All right. So, so what do we need for devices? So this is a quick summary, right? If I had a laundry list, when will I know the material I'm making is good. Now, I can go and actually make a company, get a startup company based on it, right? At what point will I know that? And I think there's a few things. So first is crystallinity for high performance. For low performance, flexible may not be important. But for high performance devices, I think we want crystalline films, completely crystalline. And that'll give us good transport properties. And we want purity. So we want low native and low non-native defects. That'll give us low background concentration, no trapping effects, those kind of things, right? And so this is very important. So whenever you see a paper, whenever I see a paper now, I think of some criteria. Is this really better than what was there before, right? And these are some criteria we can judge what's going on. Of course, the second thing is all this has to happen on a large scale, right? So if it happens in a 1 micron or a 2 micron platelet, not good enough. We need to get it on a large scale. We should be able to go make 8-inch wafers with that and make devices. And that's really important for manufacturability and cost. So of course, again, I will say, if you're doing physics or if you're inventing new devices, it doesn't matter to do large area. So everything is fine. But this is an important challenge that we have to look at. And then finally, the third one, which actually is very tough, turns out, is controlling layer thickness. So how do you make only one layer? How do you make only 2 layers? And it's very hard to get all these 3 at the same time, Very hard to get a large area, layer thickness. If you take any 2 of these, it's actually pretty hard to do, right? But if we get all of these, then we actually have a technology. Once you have that, then you can go. You can actually, the devices will be useful. Of course, at that point, these are the 2D materials. Then we have to see how they compete with existing 3D materials, which, if you remember, have all of these, okay? These 3D materials, actually, you can do all of these with them, okay? You can control the thickness, you get large area, they're very pure, and they're crystalline. So our 3D semiconductors are already good. But of course, the 2D semiconductors will give us new functionalities. That's what we look for. So this is kind of the overview of what, in terms of growth, I think many groups are trying to achieve now. They're trying to get all of these at the same time. They may state it in different ways, but this is the basic idea. So before I go ahead, I want to talk a little bit about phase diagrams. Because most material scientists, when you start exploring a new material, you want to think about phase diagrams. And I want to show the phase diagram of my favorite material, gallium nitride. Okay, so this is a phase diagram of gallium nitride. Okay, so you remember phase diagrams from material science class, or if you're device guys, probably undergrad. Temperature, and then this is gallium and nitrogen. Okay, so basically we're forming a solid solution of gallium and nitrogen. You can think of it this way. And so this phase diagram is very simple, actually. What it says is that if you have 50% equal gallium and nitrogen, you get a compound, which is GaN. You basically get woodsite or zinc blende GaN. There's actually 2 phases of GaN that are possible, but woodsite GaN is a stable one. And if you have less gallium, then you're going to get, if you have more gallium, you're going to get gallium nitride plus liquid gallium. If you have more nitrogen, you're going to get gallium nitride, 1:1, and you're going to get just nitrogen, which will just evaporate out. It'll precipitate out, right? This is actually a good thing, okay? And then, of course, if you go above a certain temperature, it'll liquefy or something. So of course, these are all, equilibrium phase diagrams. This is experimental. You can go find them for all the 2D materials. I haven't given a reference because this is from the ASM phase diagram website. Just go to Google and do ASM phase diagrams, and then you can look at phase diagrams of every material, theoretical and experimental. Super easy, right? And so it's fun to go look at these, if you don't have other things to do, I guess. But okay, so this is actually a line compound. So we call this a line compound because it's, of course, it's not exactly a line. Gallium nitride can have gallium vacancies. They act as acceptors, nitrogen vacancies, but the percentage is very small. Which means that the width of this line is really thin. It's like 0.001%. If you try to get any more nitrogen vacancies, GaN is no more going to crystallize. It's going to become basically crap, right? That's what's going to happen. All right. So what this means is when you grow gallium nitride, This is actually a growth diagram for gallium nitride from Professor Speck's group at UCSB. Whether you have less gallium or more gallium, you'll grow GaN, okay? Which means you can adjust the gallium and nitrogen just to get good growth conditions. So that means to get a smooth film or to get, so you use the gallium to nitrogen ratio in growth to improve the quality of the crystal, to improve the quality of the surface. It's not just to get gallium nitride. So you don't have to have, if you're doing MBE, you don't have to have one gallium atom, one nitrogen atom to make GaN. You can have more gallium, it's okay, because more gallium actually helps. It turns out for gallium nitride growth, more gallium helps. For gallium arsenide, more arsenic helps. So let's look at a few other semiconductors. And you'll see pattern. Indium phosphide, gallium nitride, gallium arsenide, they're all line compounds, okay? This is very important. This is why we're able to make them very pure, very low defect density. And so for binary compound semiconductors, this is pretty important. And it turns out even the pseudo-binary alloys, which are basically, if I mix aluminum and gallium with nitrogen, aluminum and gallium with arsenic, are also line compounds. This is a good thing, right? So the amount of aluminum plus the amount of gallium is equal to the number of nitrogen, to a very close degree. So now let's look at our 2D materials. And I've just listed 3, right? There's so many of them, obviously. So you can go look at all the others. But you'll see something. This is MOS2, okay? It's not a line. It's actually got some width. MOSE2 also has some width. MOTE2. WS2 is good. I know Steve works on, you've been doing WS. This is a line compound, right? So this is a good thing, right? So that means that as long as you're within some range, you're going to get WS2. Now, of course, if the amount you supply goes this way, then you'll get WS3. That's what this phase diagram is saying. Now, again, I should say these phase diagrams, they're experimentally determined. The way they determine them, they just mix powders, and then they cook them, and then they just do mass spec to find out how much was there, and then do XRD or something to find out the phases. That's what they do. It's equilibrium, and growth, very different things can happen. But it's still a good guideline. So what does this mean for us when we're growing 2D materials that we should think about? And probably also when we choose which 2D materials to work on. If you think about, let's take this MOS2 here. If you go, so what it means is when I'm growing MOS2, if I have excess sulfur, now this one here is the exact 2:1 ratio. If I have excess sulfur, I'm still going to grow MOS2 2H. I'm just going to have excess sulfur, which means I'm going to have moly vacancies, or I'm going to have sulfur interstitials, both of which are bad, right? Both of which, and if you look at the width of this is a couple of percent. Couple of percent of impurities is really bad for a semiconductor, right? It's, most technologies would say, no, that's never going to work. But of course, the phase diagram can tell us something. One thing is, if I go up, it's becoming a point here, right? So that means if I go to high temperature, maybe I can make it look like a line compound. I can reduce. And so growing at high temperature is probably good for background defects. And this is something, probably people will find empirically too. The second thing is, if you look at this line is kind of vertical here. That means if I have excess moly, if I have less sulfur, then it's okay, because having excess sulfur, the phase doesn't spread out here. Okay, so from the phase diagram, you can probably help guide the growth, because otherwise, we're just doing kind of blind experiments. But I should say that this is all very new. Again, I haven't thought about it enough. I've been talking to some people now. This is kind of new territory for semiconductors, because if you saw earlier, all the semiconductors are line compounds, right? And so working with these, we're going to have to think a little bit differently. Okay. So let's go ahead. So I want to talk about Mbe growth first. And, many of you have probably heard of this Professor Atsushi Koma at University of Tokyo. He was growing 2D materials in the 1980s, which is probably before many of, at least you were born. And I was very little then. So he was thinking about all these things. He was thinking about 2D growth, Van der Waals gap, how to grow different kinds of materials. So this is from his paper. It's a very nice paper. If you haven't seen it, probably many of you have seen it. But if you haven't, please go. You can go take a look at several of his papers. And then there's another French group also, which is also very good. They thought a lot about this stuff. I would say they're actually, we are still catching up with all the things they thought about back then, at least in the MBE field. So, this is the 4 kind of bonds shown here. So this is a 3D material. Obviously, it has the dangling bonds. And we want to think, so if you have a lattice mismatch between top material and bottom material, what's going to happen if you have very large lattice mismatch? If it's not much, you can accommodate the strain. But if it's very high, then you're going to have dangling bonds, basically misfit dislocation, misfit networks. And those are bad, right? For any material, if you have misfit networks, that's basically high defect concentration. This is basically something like metamorphic growth. Now, if you go to a 2D material, the concept is that there are no out-of-plane bonds. So, but there's a van der Waals bonding between these, and of course the bottom layer of these. And so some of the lattice matching constraints are relaxed because you don't have to worry about this, every bond finding another atom on top of it to bond to, obviously. And then when we go to 2D, 3D, which is, like I said, that's another thing I'm interested in. Professor Koma thought of that also. And what he found, they studied it. They found that if you just try to grow 2D on 3D, doesn't work so well. But if you can terminate these dangling bonds in some way with silicon, with hydrogen, gallium arsenide with selenium, and so on, then you can actually get much better epitaxy. Okay. So there were some things that they found, and I would really refer you for all. There's a lot of details in these papers. I can't cover all of them, but to papers by Koma and other groups around that time, between 84 and 98. They did a lot of work all in MBE. And so, of course, before I go ahead, I know some of you, in MBE, so I'm going to talk about MBE growth. And we are very excited about our new MBE chamber. It's been around a couple of months. Chungi is growing on it. And so this is basically an MBE chamber, a schematic. It's an ultra-high vacuum chamber. Base pressures 10 to the negative 11 torr or so. And what you can do is you can put different kinds of cells, and you basically send you can have solid elemental sources, like you can have selenium, molybdenum, tungsten, and so on. And you can send these atoms to a substrate. Then you heat up the substrate so that the atoms can move around and find the lowest energy position. That's basically the idea, right? And because it's ultra-high vacuum, and if you can procure very high purity materials, then the material you grow is going to have very high purity. And because you can control, the growth rate is very low. It's a monolayer every few seconds. So you can grow one monolayer, and then you can change and put a different monolayer. It's very simple. It's very simple. It's like an E-beam evaporator. All of you use E-beam evaporator. It's basically like an E-beam evaporator. In fact, our new MBE is an E-beam evaporator because our moly and tungsten are E-beam sources. Okay, so it's just a very expensive E-beam evaporator. That's about it. But the nice thing about MBE compared to MOCVD is that it allows for some very nice in situ monitoring. So one is READ, which is reflected. It's an electron diffraction. I'll talk about it later. But basically, this gives you it gives you an electron diffraction image of the surface. And this is really great because what it gives you is it gives you a diffraction image of the 2D surface, which is like a 2D crystal, right? But we are growing 2D crystals, so it's perfect. So with READ, we can actually say everything that we need to know about our 2D crystal with READ in an MBE. So as you're growing it, you can see what you're growing. And I'll show later, it's been used really well by many groups now. And second is Raman. So in our system, we also have, we have installed the READ. We're going to install Raman so that we can do in situ Raman, so that while we are growing, we can actually look at the Raman spectra, because that also can give you all this information. Of course, you could probably do this in an MOCVD system too. It's not unique to MBE. So I wanted to show you some of the early work on van der Waals epitaxy. And so this is basically, these are READ images. I'm going to show you a lot of READ images. So before I go on, let me just tell you what these READ images are. These READ images are basically diffraction images, and they show up as streaks. And without going into too much of the details, the spacing between the streaks corresponds to the atomic lines on the 2D crystal. Okay, so if you have an atomic spacing in some direction, this is basically the Fourier transform of the spacing. And in very early, what Koma's group did is they started looking at growth of 2D materials on 2D, MOSE2 on SNS2. Both are layered materials with pretty high lattice mismatch. And what they found is that depending on the growth conditions, you can get crystalline MOSE2 on SNS2. So let me show you what's happening over here. Okay. So let's take this. This is just SNS2. This is the read image. And what these streaks are corresponding to is basically the spacing. You shoot the electrons in a certain direction. You get the diffraction image. The lines, you know, the atomic lines that are there, it's giving you a Fourier transform of that. And then, of course, what they do is they put selenium on the surface, and then they start growing the moly. And you can see, initially, you see this double line here, right? And the double line is basically both it's partial coverage. MOSE2 has not covered it completely, so you have some MOSE2, but you can also see the underlying SNS2. You can see both of them. This is not just in 2D growth. This will also happen, you know, when we grow highly mismatched films like indium nitride on GaN or so on. You can see both the read, because now what this means is some of the surface it's partially covered. We have islands. That's what it means, right? So it's very powerful, you see, because you're able to see while growing what's going on in there. And of course, from the spacing, if you take 1 over the spacing, it gives you the lattice constant. Okay. Then when it's fully covered, now this is the MOS2 read, right? And so this paper is nice. You can look at it, but what they found is that even with the lattice mismatch, they were able to do epitaxy. They got high-quality films, and they were able to confirm that within 1%, it's aligned. Okay, so that means it's a crystalline film. That means top film, bottom film are both in epitaxy. That means they're registered to each other. That's a good thing. But there were some other interesting things, and I just highlighted this. You probably can't read it from the back, but basically what this says is, although our first thought about van der Waals epitaxy was that lattice matching would not be a factor, further thought reveals that there are still more and less stable sites for interactions. And so what this means is, even though we keep saying that in van der Waals epitaxy it doesn't matter, lattice mismatch, the details are in this paper, and you can probably go look at it, but basically it's not that simple. When you grow lattice mismatch heterostructures, every atom is trying to be on top of the other atom. Then because of the mismatch, some of the atoms are going to be displaced. And that's a problem, because then the growth of those is going to be different from these. And so I think this has not been understood completely. There was some work in the 90s, but now again we have to think about it because it's become important now. So we have to think about, how does van der Waals epitaxy take place when it's lattice matched, when it's not lattice matched? How does the surface impact it? And so I think I need to move a little bit faster now. So then I want to show you some results of 2D on 3D. And again, this is from 1993. And again, you can see here, this is actually the silicon 111. So this is gallium selenide, which is 2D, 2H gallium selenide grown on silicon 111. And so what we're showing, this is basically the read of silicon along two directions, 101 bar and 112 bar. So basically, 90 degrees to each other. And so what's going on here? So basically, you have silicon. You terminate it with hydrogen using a hydrogen plasma. And then after that, you can grow gallium selenide on it. And what's important here, again, to look at is that the gallium selenide is both in this direction, okay, in the 101 bar direction and the 112 bar direction. The gallium selenide has the same crystal registry. Okay? So that means you can grow crystalline gallium selenide on silicon. Okay? And so essentially, if you look at the reason I'm saying this is, I talked about Mbe first. When you see the CVD, you'll see a lot of the CVD work. It's very difficult to get epitaxial registry. They're all polycrystalline, right? But this was already done. People got epitaxial crystalline films a long time ago. These are thick films. Okay. So I'm going to talk a little bit, and again, this is more recent work. This is from the Institute for Nanoscience in Athens, Greece. This group, I'd encourage you to look at several. They've written several papers in this area looking at 2D on 3D epitaxy. This is one of them that I found interesting because it's sort of what we're trying to do, grow 2D heterostructures on aluminum nitride. And it turns out the nitrides have very small lattice mismatch with the 2D materials. That's one of the reasons we're interested. And so you can see here, without going into the details, basically they're able to get MOSE2 films directly on ALN. Okay, so they're able to grow very good quality MOSE2 on ALN. And so I think this is, what it shows is that there may be another route to getting very high quality MOSE2, which is by choosing the right substrate. Okay, that might be the key thing over here. This is some of our own work. This is something, for those of you who are doing MBE or doing material growth, something that Chung-Hee has been discovering. So we've been trying to grow on several substrates, on sapphire as well as GaN. And what we found is that we can start with sapphire. This is a sapphire reed out here along the 101 bar O. And what we find is when we grow gallium selenide, it's not so clear here. Our reed camera is out, so I think this is taken with a phone, this picture. But the phone cameras are working pretty well, though. But basically, there's two lines, okay? So basically, you have the lattice of gallium selenide, which is a hexagonal lattice. But when you grow on sapphire, it turns out you get both the lattice that's on the sapphire and then rotated 30 degrees. So you get domains of both, and so both of them show up here. Okay? That's not a good thing. We want single crystal, right? We want to have one phase of gallium selenide. And of course, depending on the growth conditions, you can also get gallium 2 Se3. So all these things, these are all the bad things that can happen, right, in Mbe growth. But it's important to think about it because when you look at the reed, it may look that it's fine, but it's not because you're actually seeing both. And similarly, when we grow on GaN, also it turns out the same thing happens. But Chung-Hee has been able to fix this problem. And so now you can see here, this is basically the GaN 112 bar O direction, gallium selenide 112 bar O, and then out here 101 bar gallium selenide. So now we have a gallium selenide film that's completely crystalline on gallium nitride. Okay? Of course, the reason we're doing gallium, we started doing gallium selenide was our E-beam source had not come in. Gallium selenide is a very painful material to work on. The moment you take it out of the chamber, it oxidizes and it's gone. So it's, maybe it's useful for some transient electronics, but it's just a very painful material to work on. So we're going to move on to MOSE2. But we're learning a lot about how to do these things. And I encourage you can talk to Chung-Hee about all the details about how this happens. And again, so I just wanted to show some of the TEMs from that same group. This is the MOSE2 on ALN, and you can see here, this is very high quality crystalline MOSE2 grown on ALN. Okay. So I find this all very encouraging, and there's many other groups actually now. Cornell, Devdeep Jaina's group is working on MBE. Sanjay Banerjee's group is working. I couldn't talk about their results, but there's some very nice work going on in MBE, trying to make these large area films. So I'd like to jump over to CVD. And so let's see. So there's many ways of doing CVD. I'm gonna skip a few. Okay, I'm sorry because I'm running out of time. But one that caught my eye recently was a very nice one, which is basically this paper on getting wafer scale single layer growth. And this is basically using it's basically CVD, but they've used these. But it's different from many of the CVD, which are basically a closed tube, and then you cook everything inside. This is basically injected gas, which is probably, I think, something like what you're getting here. And so this is closer to MOCVD growth of 3/5. And I think eventually they can control the doping and so on. But the results are very interesting. They can actually get over the entire wafer. This is over the entire wafer. They were able to get MOS2 growth with mobility of 30, which is actually really good. Single monolayer coverage, and it was on SiO2, which is not epitaxial, it's amorphous, right? But when it's amorphous, what does that mean? It means that when you look at, this is the grain structure, okay, of the 2D material. These are all different grains. And so, if you start on an amorphous material, you're not going to get a crystalline semiconductor, right? That's pretty simple. Asking the MOS2 to grow crystalline on SiO2 would be like, asking 10 monkeys to type out a poem or something. It's just not possible, right? It doesn't know how to do it. It's random. So we have to have epitaxial. But however, if you think about this, this is already really good, right? Because we can get single layer with a mobility of 30. This is really great because now I think this is ready for actually some applications. Even though they're polycrystalline, they have good mobility, they're optically active. You can probably make different kinds of devices with these. So I think, like I said, it's not necessary to have crystalline for every application. A lot of TFTs have very low mobility, so they work really well. All your screens that you have, they're all TFTs, flexible displays. So this is an amazing result, I think. And there's other groups also. Again, don't want to say this is the only one. There's other groups, but this is a very, very exciting result because it's over such a large area. There's also been some very interesting work making heterostructures, and I think a lot of the heterostructure work, it's been difficult to get it over the entire wafer. But this is some nice recent work which shows that you can actually make, it's more a proof of concept, that you can actually put one material on the other. But I would say if you go back to Coma's papers and so on, I think the proof of concept was established. They already grew them over large areas. But I think it's still, people are starting to look at devices and so on with these. And you're probably looking at different devices with 2D heterostructures, looking at trying to make TFETs and those kind of things. Very interesting things going on. But again, these triangular features which are very common, the reason they're forming is basically you nucleate at some site on the SiO2, and then each of these grains basically grows out, along the facet that has the, depending on the growth rate, you get these facets, and then they grow out. And so each crystal, each of these domains is single crystal. But it's eventually when they join, then you're going to have grain boundaries, and that's not going to be good for transport or for device repeatability, all that stuff. And so if we are interested in crystalline order in all directions, in plane and out of plane, we don't just want growth. We don't just want things just growing out like that. We want epitaxy, right? So epitaxy means every atom here has to see what's below it and then follow it and go sit there, right? That's epitaxy, basically. And so how to do epitaxy? And one way to do epitaxy is, of course, to start with 2D materials. But there are, 2D substrates are not so, there's some, mica is there, there are some layered substrates. But 3D substrates are much more common. They're very easily available to us. Things like sapphire, gallium nitride, you can buy them very easily. And so as long as we can find some substrates that match well, we can use them. And so, for example, gallium nitride turns out is very close, 1% lattice mismatch with MOS2, with a lot of these materials. So as long as you can adjust the growth, you can use this. And so I'm going to try to talk a little bit about when you grow on crystalline materials, what happens in CVD. And so this is how we do our growth. This is a kind of a primitive technique. We put moly metal on sapphire with sputtering, and we put it in a quartz tube with MOS2 powder, and we heat it up to 1100. Temperature is very important. And then we cool it down very slowly. That's also very important. And then if you do those two things, you can actually get crystalline films. And so how do we know it's crystalline? So this is an XRD. And you can see here, this is on sapphire, okay? We can't do it on GaN. High temperature, GaN will decompose. But this is sapphire out here, and you can see the sapphire peak nice and sharp. These are the MOS2 peaks, 002, 004, 006, 008. And they're broad not because of the quality, they're actually broad because it's a thin film, so it's thickness-related broadening, right? And so you can actually get this, but this is not a big deal. Actually, almost everyone who grows layered materials will get this XRD, because layered materials want to grow this way, okay? I think what's more interesting is looking at out-of-plane order. And so this is basically, we're looking at the XRD in an off-axis direction, okay? So we're looking at a plane that's inclined to the basal plane. So this is a basal plane. We're looking at some inclined plane here. And so these are the sapphire peaks here. You can see there's 3-fold symmetry of sapphire. And then that's MOS2. You can see the 6-fold symmetry. So what this is telling us is using the CVD growth, which is very cheap compared to Mbe, right? It's just a quartz tube furnace. You can actually get 6-fold symmetry. And why does this happen? It turns out that even though sapphire would seem to have a different lattice count, in a similar way that GaN grows on sapphire, it's a 30-degree rotation of the MOS2. When the MOS2 rotates by 30 degrees, it actually has some kind of commensurate match. 7 of the MOS2 unit cells and 8 of the sapphire unit cells, they basically match up. And so you get a commensurate match. And this is very common in these kind of highly mismatched systems. But essentially, it looks like the MOS2 atoms know where to go to arrange themselves. And this is just a high-resolution TEM of that same, if you pull it out and just look at it, very good crystalline order. This is over larger and larger fields. But I would say that high-resolution TEM is not the best way to judge this because XRD is taken over centimeters. The XRD slit width is much larger. And so what this is telling us, although this picture looks very impressive, the XRD to me is a more valuable tool to tell me what's going on over a large area. Okay, so I'm going to end in exactly 2 minutes. That's how I'm going to give myself. Talking about doping of 2D materials. So doping is very important, right? I think if you don't have doping, it's very difficult to make devices, right? So, and so there have been some very interesting approaches for doping because you have a 2D material, so you can just put on the surface. So this is potassium, chloride, bromide, different kinds of things. That chloride doping is different. I think they dip it in dichloroethane, and then they soak it, and then they anneal it. And they get N-type. There's also N-type, and basically you're replacing sulfur with something to the right. We've also been looking at this. We've tried to replace, but we want to do in situ because we think, of course, ex situ means you can pattern it. That's really cool. In situ is interesting if you're trying to make heterostructures, right, if you can dope it. And so we've been trying to do in situ doping. And so this is some of the thing that we did. Basically, we took moly. We put niobium in the middle. Why did we choose niobium? Because niobium is to the left of moly. So it's probably an acceptor. And there's some work. Actually, we're not the first people. Back in the 70s or 80s, people were growing P-type MOS2 with niobium. And so it turns out it works. Okay, you can get P-type MOS2. The structural quality actually is not as good at high doping. That it degrades as you dope higher and higher. It's still, it looks okay if you do a TEM, but if you actually do XRD off-axis at high doping, it's not good. But at low doping, 10 to the 17, it's actually fairly good. And I'm sorry, I'm rushing through these. But I guess what I wanted to show you was this. This is the absorbance spectra of the MOS2, both the P-type and the undoped. Both of them show the direct band edge as expected. And the Raman is not degraded significantly. So now we can dope it, but obviously a lot more work has to be done. We can't just we have to control the doping. We have to understand a lot of the parameters and so on. But I just want to show you that we can use this doping, and we take the P-type MOS and put it on GaN. We can basically make PN diodes, which work fairly well, and we can actually extract what the band diagram looks like. And so this is a new kind of heterostructure. Many people are working on this, not just us, combining 2D and 3D materials. This is from a couple of years ago. This is what the TEM looks like. This is transferred, right? And so the interface is going to be dirty for sure. Well, if you dope both of them very heavily, then you can actually make tunnel junctions. So this is basically an Esaki diode with P plus MOS2 and N plus GaN. And you can see here, you can see the characteristic NDR characteristics. And this is large area, right? So we actually just use stepper lithography to pattern everything. And finally, I said, I was talking about mechanical transfer. This is some recent work where people have used HBN. So this is boron nitride as a template for growing gallium nitride devices. And what they've got is the boron nitride, of course, it's layered material. They grow it on sapphire, and then they grow this device. And then they can basically remove the device. And then they can remove it and put it on any substrate. And they're able to grow HEMS, LEDs. This is work from NTT. And I think this is very exciting because if you can use 2D materials as templates for other things, I know it's not using the electronic functionality of 2D materials, but there's no other, it's very difficult otherwise to do this kind of thing. It's very complicated. And so this is a very new and interesting approach that's starting out. So I'm going to stop with a summary. I think high quality growth is very important. It's probably one of the most important problems right now. But there's so many interesting problems, fundamental problems, and then also technological problems we have to solve, ranging from understanding lattice mismatch, phase diagrams, all the way to doping and defects. And once we do all this, we can probably make really good devices. So with that, I'll stop and take any questions. Thanks.
Your questions? Hopefully leaving some time for questions.
You mentioned briefly that there's some risk of adsorbents causing some sort of unintended doping.
Oh.
Comment on that a little bit?
No, I think yeah. So I think the question is a risk of adsorbates causing unintentional doping. Now, I think in the paper, the potassium doping paper was intentional. They put potassium to actually dope the material. I guess what I was concerned about is the long-term stability, because if you have to actually make a device technology, you have to do passivation, you have to do metal contacts, those kind of things. I don't know how compatible that's going to be with other device technologies. But I think it's a very interesting way because you can put the doping wherever you want, kind of like ion implantation. So it's very interesting, yeah.
Can I actually ask a question
Sure.
about strain?
Yeah.
When you're growing these epitaxially, there is some lattice mismatch,
Yeah.
right?
Yeah.
So do these get strained in the same way that 3D on 3D would be strained, or not?
Yeah, so I think the understanding is that they don't get strained. They grow relaxed from the first layer on. And but instead, what happens is, let's say there's a 9:10 lattice mismatch, right? 10% lattice mismatch. Then what's going to happen is that for every if the top layer is completely relaxed, every atom doesn't see the same. When it looks down, it's not the same for every atom because it's like a commensurate, right? So every 90th atom is actually going to look the same when you have 9:10, right? So something like that. So now, because of that, that affects the growth. Because in some areas, you may get different growth rates than the other. And so I think that's an issue. But the strain itself is not. I think coma, I should have shown that. But in coma, they showed they grew 50% lattice mismatch. And they were able to grow layers that were completely relaxed, one on top of the other.
But still with ordering without a grain structure, then still. So you don't have the strain, but it still is single grain.
That's right. So I think so that's where I think it cannot happen, right? So if you have to have single crystal, you have to have something like what we did with the sapphire, where it is actually everywhere, but it's a commensurate. And this people do in 3-5 epitaxy. They grow commensurate, kind of structures. So that might work. But I think really in the end, it's best to be lattice matched. So I think you want to find a lattice matched substrate. So there's no problem with epitaxy. So the epitaxial relationship is going to be very clear. And that's why I think, there are materials that, luckily for us, there are 3D materials which are very commonly available, like zinc oxide, gallium nitride, which have same lattice structure as these 2D materials. And so that's a good thing for us. We can probably try those. Yeah.
I just want to briefly comment on the surface roughness and uniformity of those genes.
Oh, which ones? I showed many. So the CVD films. The CVD films, yeah. So the CVD films, uniform means they're everywhere. The surface roughness is actually on a 5-micron scale is, I think, approximately half a nanometer, right? Approximately half nanometer, 0.5 nanometer, which is kind of similar to a lot of other 3D semiconductors, half a nanometer kind of roughness. Yeah.
Other questions?
I came a little late and I missed your talk about your part about doping. But,
Okay,
I was
yeah.
wondering if you could, I heard you say something about doping not being quite stable.
No, I guess I was just saying, so I guess what I was saying is that ex situ doping is a big advantage. If you can just deposit things on the surface and dope, kind of from the surface, like a surface donor. So if that works, that's good. But then you have to come up with a compatible process next to it. Because obviously you can't leave the surface like that open. You have to put something else on top. And so the step that comes later, whether it's some passivation step or something else, it may not be stable when you do that. So I don't know, for example, when you put potassium, if I passivate the device with silicon nitride, whether it's still going to be stable. So, but yeah.
You know if it's possible to dope with group 3, like in the 2 6s, can you dope with group 3 or group 5s on the anion site? Anyone tried these types of things?
Oh yeah, I think so. I think the 2 6s.
I'm just talking about ADMOS too. In the van der Waals materials,
right.
Can you dope them substitutionally by going down to the next?
Yeah. So sorry, I rushed through the doping part. Obviously bad planning. So, for the MOS2, let me just jump back here. Where's that thing? Yeah. I think so obviously the candidates would, I guess, be niobium because it's similar size, and probably manganese would be N-type. And so I think both of these, so definitely niobium we've tried and it's P-type. I think there's some report of manganese being N-type. At least that's probably in DFT theory. I don't know if experimentally. We've tried it and it hasn't worked, but that doesn't mean it's not going to work. It probably just means we have to try more. We've tried manganese. The other one is, with moly, obviously rhenium is going to be hard because of the size difference, but that could be another thing to try. I think we did get a sputter source, but for tungsten, that'll be much easier to put rhenium to dope it. But right now, I think the only thing confirmed by several groups now is the niobium on moly. That works as expected. But then there's chlorine on sulfur that works too. So I think you can go there also. Yeah.
Any last questions? Okay, let's thank